Hi, Mick McQuaid here to talk about data visualization and in particular use cases for data visualization and to focus on Tufte's 2001 book, The Visual Display of Quantitative Information. This is the second edition of a book that was originally released in the 1980s, and this is a book that popularized data visualization, although the content was not really new. Rather, it collected a lot of previous work and presented it in an attractive form. Kind of rediscovered a lot of previous work. For example, Anscombe's quartet. Francis Anscombe was part of the exploratory data analysis revolution of the 70s. He presented an example that has come to be called Anscombe's quartet, highlighting the need for data visualization under the then popular banner of exploratory data analysis. Anscombe constructed 4 data sets that share the same summary statistics. No statistics differ here among the 4 data sets. We would have to inspect statistics called residuals to find numbers that could distinguish between these data sets. Yet we can very easily distinguish between the 4 data sets by examining scatter plots. In fact, they could hardly be more different. So we see that simple regression analysis does not help with curves and outliers. The scatter plot is a powerful graphic form because it shows the 2 axes at the same time. The marginal distributions represented by the tick marks cannot detect some outliers such as point A. Among the preposterous theories of the Great Depression was the idea that it was caused by sunspots. This bivariate graphic illustrates the principle of garbage in, garbage out, but it has a redeeming feature in that it illustrates how we can portray 3 different scales in a single picture. Notice the scale on the left is for reading the sunspot data, while there are 2 scales on the right, one for New York and one for London. This is the second most famous graphic in Tufte's book. It shows how a data visualization could have, but unfortunately did not, halt the spread of cholera during an infamous epidemic in London in 1854. The man credited with stopping the epidemic, John Snow, realized afterward that plotting the deaths from cholera on a map highlighted the source of the infection, a water pump marked with an X next to the D in the words Broad Street on the map. He publicized the map afterward, raising awareness of the power of cartographic visualization. The actual means by which he spotted the infected water pump was via word of mouth and the assistance of a priest who was tending to the dying cholera victims in the area. The full story is detailed in a fascinating book called The Ghost Map by Stephen Berlin Johnson. This weather summary depicts 1,888 numbers in a way that makes it easy to relate them. A vast number of questions can be answered with this summary that would be difficult to answer with tables of numbers. Of course, this summary was created in an era when newspapers had no capacity to use color, and the values, in Beltin's sense of the word values, obscure the meaning because of that, and because they have been reproduced several times, by Tufte first, then by a scanner, and then by the projector. The original is surely as easily readable as any newspaper graphic from 1981. This graphic shows how U.S. representatives exploit their franking privileges just before re-election time. And for international students, maybe I should explain, franking privileges mean that they get the use of free stamps, free postage. They can mail things out for free. And they do it primarily just before re-election time. Tufte says that that picture is worth at least 700 words, which is the length of this New York Times story, providing basically the same message. Now we come to the most celebrated data visualization in Tufte's book, Charles-Joseph Minard's map of Napoleon's Russian campaign. It shows the location in 2 dimensions and the direction and the size of the Grande Armée as it was shrunk by the Russian winter. It also plots temperature and dates for a total of 6 variables if you count location as 2. This map has become the stairway to heaven of data visualization. Stairway to Heaven is a famous song enjoyed by beginner guitar players in the USA. Many guitar shops have posted signs saying, "No Stairway to Heaven," because they don't want to listen to any more beginners trying out Stairway to Heaven on their showroom guitars. Likewise, I feel a little silly including it in a slideshow since it is the most overused information graphic of the past 30 years. In fact, there's even been a contest to write software to reproduce it. This graphic illustrates the principle of faceting, which Tufte refers to as small multiples. This has been superseded by animation in the past decade, but is still an effective way to show change over time in print or on static screen displays. Now, I don't want to belabor the faceting principle since it can often be accomplished via animation today, but this is a really great example where we see on the horizontal axis and elevation on the vertical axis, we see time on the horizontal axis and elevation on the vertical axis, and the life stages of the beetle as the facets or small multiples. Tufte repeatedly extols the virtues of scatter plots throughout his book, providing examples like this one showing how it has been used to portray cause and effect. So the cause being, of course, cigarette consumption, the cause being cigarette consumption and the effect being deaths per million. Tufte shows a number of untruthful visualizations to spotlight the notion of graphical integrity. By the way, this is the title of a book by former U.S. Senator Al Franken. Here's a page from a company's report, and if you look closely, you can see that the left panel bars appear to have a baseline of 0, while the center panel bars have a baseline of about minus 4.2 million. Income isn't quite working out for them, but they don't really want to emphasize that. Payments to travel agents appear to have declined precipitously in 1978, but if you look closely, you'll see that 1978 figures are for 6 months only. Tufte posits a measure called a lie factor, which is the ratio of depicted effect size to data effect size. Here it is quite large, and the picture displays a few anomalies as well. For instance, the road is receding into the past instead of forward into the future. The numbers on the right shrink, but the numbers on the left don't shrink. The shrinking of the numbers on the right is at a different rate than the shrinking of the pavement. The road width increases 783%, while the data shows a desired increase of 53%. So this ratio represents a lie factor of 14.8. Here's the same data without the lie factor, and Tufte takes this opportunity to complain about decorations of graphics, which he calls a sure sign of a hack at work. Here's an example of using a truncated period to pretend a decline is happening. The graphic on the left was used by the National Science Foundation to complain about funding for science in the USA. The corrected version uses a commensurate time scale at the right to tell a different story. Tufte takes this opportunity to enunciate the principle that you should show data variation, not design variation. Notice that the scale for money changes quite drastically for 1979, the year that this graphic appeared. Here, Time magazine shows an increase of 454% with a picture depicting an increase of 4,280%. Tufte includes a number of other oil price increase graphics and notes that they mostly use inflated dollars, increasing the lie factor since the price in adjusted dollars changed much less in this time period. This graphic from The Economist uses inflation-adjusted dollars, showing that the real price actually declined for several years in the 70s. Tufte uses this graphic to introduce the term chart junk, meaning decorations that distract you from understanding the graphic. The chart junk here includes the 3D effect and the horizontal arrows at left and vertical arrows at right, both of which emphasize growth. Tufte's prescription for improvement is in two parts. First, remove the chart junk, leading to a calmer graphic. Second, adjust for inflation, leading to a different conclusion about growth. Don't use area to depict univariate data. Don't let the depicted dimensions exceed the data dimensions. This example solves the problem of aspect ratio neatly by coiling up the horizontal dimension into a spiral. The spiral also seems to place the furthest past at the greatest distance and most diminished size. The result is an optical effect that works with the data rather than against it. It looks like enforcement had a drastic impact. But what if you look at some context around it? And what if you looked at even more context? So context is key. Data-ink ratio. So Tufte uses the notion of data-ink ratio as kind of a principle. Other authors, including Wilkinson, whom we've talked about, have shown that that principle has its limits. This display compares length at reproduction with generation time for organisms as diverse as fruit flies and giant sequoia trees, which are the largest living organism. The data-ink ratio is high in the sense that most of the ink on the display is devoted to data. Very little ink is devoted to anything else. Notice that the scale is logarithmic on both axes, which is another trick for compressing a dimension to fit the display, and a much more common one than the previously displayed spiral. Here's a display that looks slightly worse than it should, but only slightly. Most of the problem is the ink-heavy grid. You can make out a few of the points in the upper right, but in the original, I promise you I could just barely make out a few more points. Removing the grid fixes the problem and makes it easier to concentrate on the data. At left is a published picture of the results of some experiments on the taste buds of human tongue. The basic idea is that is intended to be conveyed is how much taller the bar on the left is than the bar on the right, as well as the variability in the bars, which is small except for 2 at the lower left. By removing the material shown in the center panel and leaving only as much as is necessary, gives the display in the right panel, which is much easier to read and much easier to make comparisons. Here's a comparison of chemical elements by their atomic numbers and volumes. Tufte describes it as bombing a patch of mosquitoes. Can we improve it by removing the grid? Yes, removing the grid makes it even reasonable to add a few of the standard abbreviations for some of the elements and to give a little more information. I mentioned before that Tufte uses the term chart junk to denote elements that should be removed. Let's look at a few. I double dare you to stare at this for a long time. No, don't, seriously. It will start shimmering after a while and can make it hard to concentrate. Still, it is used in many data visualizations. Believe it or not, these are Mexican government statistics on textiles in 1927. It looks like an old TV test pattern, and it is a challenge to those trying to concentrate. Why so much grid? That's often a question about graphics. Take these, for example. Removing chart junk is just grid removal in this case, or grid lightening. But sometimes it's much more. Tufte nominates this as the worst graphic of all time. It is supposed to represent the age structure of college enrollment. The older students are shown in blue and red, and the younger students are shown in green and yellow. And the basic point is that more older students are enrolling and fewer younger students are enrolling, but it is puzzling. Last, I'd like to show a few examples of multifunctioning elements in information graphics. This data visualization was completed with nothing but a typewriter and ruler and published at the end of World War I, and it shows the presence in the European War of divisions of the American Army and when they appeared in the war. Chernoff faces are an interesting way to represent multivariate data. Hermann Chernoff realized that people are quite sensitive to differences in faces in comparison with their ability to distinguish features of random geometric objects. So ostensibly you can see the outlier here much more readily than you could if it were depicted by a random geometric object. And by the way, I should mention about that last one, let me just mention that Leland Wilkinson implemented this in a statistics program called iste782, and I think he may have also implemented it in SPSS. Here is a bar chart that appears in one of the most prestigious journals, JASA, Journal of the American Statistical Association. Does it need this much ink? Can we shift some of the ink to multifunctioning elements? Why not allow the numbers to function as lines, both the vertical axis and the main data curve? That brings us to the end of this very brief review of Tufte's very famous visual display of quantitative information. I thank you for your attention. Until next time.